16. And grad students about the same. Actually, grad students a bit lower, a little bit. Okay. There's a question. The outline of midterm will be repeated. I don't understand your question. So basically, the final will be a comprehensive exam that covers all the materials. Okay. Any other question about the exam? Okay. As I mentioned, if you want to know the details about your midterm, talk to your TA. Okay. And afterwards, if you still have questions, you can come talk to me. It's between 16 to 17 out of 27. So total there are 27 marks. Okay, and its weight will be 30% when we compute our final grade. Okay, I believe it's 30, 40, right? Yeah, it's in my course outline. Okay, so yeah, so much for the exams. Okay, so this new topic will be the what we are interested in. Many of you might register this course for those magic words, right? The neural networks. Okay, so that's what what we're going to talk about today. And there's no mystery there. So we'll this is an outline. We'll look at why we are doing the multi-layer neural networks and the neural network structure, and give some few examples, and also probably currently the most famous algorithm in the world, backpropagation. Okay, but it's really not mathematically. It's not complex. Okay, so after these 2 weeks, I hope you have good grasp of the this backpropagation algorithm. Okay, so I hope you are still fresh in terms of linear discrimination function. The linear discrimination function we talk about basically in terms of learning, right? In terms of learning, we have several criteria. We start with perceptron criteria, and then it's okay. You still keep asking me about midterm. Okay, so what I'm saying is that please, if you have questions, talk to your TA first. Okay, I understand that sometimes you probably what you say in terms of mark probably is not different. It's not exactly your expectation, right? So, but please talk to your TA first. There are students who have already talked to the TA and emailed me saying that after they talk to TA, they realize their mistakes. Okay, and it's it's computer marked, and then we examine all the marking. Okay, And specifically, and this time we actually gave you some leeway in terms of we particularly saying that you need to have 2 decimal points, right? This time, actually, if you don't do that, you probably got the mark. Okay, we manually go through those things. But next time, I hope you can read the instructions carefully. Okay, so, okay, I guess for everyone who probably missed a few minutes, the first few minutes, again, okay, let me repeat. For midterm, any questions you might have on your particular answers, talk to the TA first, okay, please. Don't want to burden the TA. I'm not sure what you mean, okay? If you look at the announcement, basically, what if you don't have to talk to them if you know what went wrong, right? But if you have questions, okay, please talk to them. Every one of you made your own mistakes, right? If I'm talking about the mistake, you know, anyway, okay. So I think you know what I mean, okay? If you don't know what went wrong with your exam, talk to TA, okay? And for most questions, you have already seen that in your in the notes or practice, right? So yeah, any other questions? Okay, I want you to focus on the new materials. So next time I probably should release after this class. Anyway, so I understand the anxiety, but I do want you to come back and focus on class. Any more questions? Ask now. Okay, so yeah, put that on the back of your mind. Okay, the midterm, and you can go to the lab, talk to TA, and I'm sure you will you'll be satisfied with your questions. Okay, but meanwhile, let's come back to focus on our class, our materials. How about that? Okay, thank you. Okay, so yeah, the exam is basically serve as what we're talking about here, right? It's a criteria. So basically, from the exam and then we have the criteria, and then we can adjust that according to the error, right? If that's it's basically supervised. So we have several criteria: the perceptron criteria, squared error criteria, and normalized squared error criteria. And most of them basically are measuring errors from the misclassified samples, right? All these JP, JQ, JR, we only calculate the errors from misclassified samples. And then we have square error method, right? The square error method is actually the method that we compute the error from all training samples. It's easier to operate, right? That's minimum square. We have minimum square error. And particularly, we reviewed the least square method, right? So basically, we want all the samples close to a line. And then we have a linear equation to solve. You have all learned that problem, the least square problem, in your linear algebra course. If you forgot, check the book. Okay, at that time, you probably don't know the usage of that. So here is one application usage. And for that particular least square question, we are able to find out the closed form solution, which is pseudo-inverse. Okay, so we did test that in midterm, so the pseudo-inverse. And for pseudo-inverse, we know that it's not really an inverse because inverse only hold for square matrix, right? Only square matrix can possibly have the inverse a matrix inverse. So this one for this square is actually it's a tall matrix, right? You have more rows than columns. Okay, then we have this pseudo inverse. But pseudo inverse has the similar property as the inverse. That is, if you multiply the pseudo inverse on the right of your matrix A, right? Basically, A multiply as the pseudo inverse of A, you will get the I matrix as well. Okay, so that's one thing you can do when you do exam. So basically, verify you don't have to calculate the inverse. You just verify whether one is the inverse. One matrix is an inverse of another. Just multiply the two to see whether you can get the identity matrix, right? So that's closed form solution for that linear least square problem. But in the most machine learning method, like in neural network in general, we don't have the closed form solution. And most likely, okay, what we need to do is we will have to use an iterative learning method. Okay, iterative learning method in all these LDS method, we have a iterative learning method, and particularly for the mean square error, we have this least mean square error method, LMS method. LMS method is basically the foundation of the today's AI machine learning. Okay, it's basically we use instantaneous. We use one sample error to represent all the errors, right? To represent the average error, and then we have LMS method, and we'll get back to that again later when we talk about the learning of the neural network. Okay, also the iterative method has its advantage in comparison to the closed form method. Is the closed form method, you do need to compute a matrix inverse. That matrix can be a huge matrix. Okay, if it's very large, then it's hard. You need a lot of memory, and it's hard to compute. And then when you use this iterative method, then you don't need that much memory. Okay. So even if you have the closed form solution, sometimes the iterative learning method is often useful. Okay, so the way to do the LDF is we assume the form of the classification boundary, right? We assume the form is the linear, and then we try to modify the weight. That is called training, right? We modify the weight such that we can achieve the optimal result in terms of criteria function, right? It can be minimum error or minimum squared error. And the linear boundary in general is it's very useful in real world problems. Okay, and still in data analysis, 90% or more, we are indeed using the linear discriminator to handle the data analytics problems. Okay. But if you want to get a very good classification result, okay, in some demanding applications, the linear boundary may not be good enough. Let me explain what that means. Okay, so in terms of the limitation of the linear method. So if you have classes, right? If you have classes which are linearly separable, okay, or close to linear separable, that means you can have a line that you can classify the two classes, right? So, but it's possibly we had an example, like if you have, for example, all this guy here, right, and then you have another class around it. This one is going to be linearly inseparable because however you draw a line, it's not going to separate these two classes. And basically, in this case, we said that there's a smart way to choose your to transform the data, that it could become linearly separable, right? So one example is if you use this as the coordinate is also important, right? So assuming if you transform it using this coordinate system, okay, origin at the middle, and then you can say basically if you convert this into a polar coordinate, okay, you will be discriminate using the r, basically the distance to the origin, right? Then in this case, if you transform it, let's say this is r and this is theta, right? In that case, you will say that the cross is probably in this area, and the circles in this area, and then you can still use the linear discrimination to do it, okay? But probably sometimes you're not so lucky, okay? Or you it's not obvious what nonlinear transformation you should use to make it linear, right? Okay, so it's not easy to choose how to choose these nonlinear functions. Right? It is not easy to choose those nonlinear functions. So that is a problem we want to solve. Okay. So that's one motivation for neural network. And particularly, okay, so if we look at the structure of the LDF, right, linear discrimination, so what we have is actually, if you think about it, so it's pure linear function, right? It's basically, it looks like this, okay? So you have your x1 to xd, right? You have d dimension. This is your feature vector. And you also, if you remember, we also have the bias 1, right? So this is bias unit. We have a bias unit, right? So 1, and then this is like 1. This is W0, W1, and until this is WD, right? Remember that. So basically here what we get is GX. Okay, and in terms of classification, right? In terms of classification, what we are doing, the last step actually, we look at whether GX is larger or smaller than 0, right? Okay, so basically we're computing whether this is larger or smaller than 0. That, in effect, is equivalent to a unit that a thresholding unit. Okay, so the output in this case, okay, if we redraw this, it becomes this form. So still we have this 1, right? X1, XD. This is called augmentation, right? So basically, plus them together, right? It's W0, W1, and here, WD, right? And then we indeed have a nonlinear unit. This is nonlinear unit. then we have this output, right? So this particular one is actually kind of construct, we call it perceptron. Okay, or in neural network context, we call it neuron. Okay, with one nonlinear unit. Okay. So if this function, right? If this function is kind of this type of not a threshold function, but a nonlinear function as a sigmoid function. Okay, if nonlinear function is sigmoid function. Okay, I will we'll discuss the detail of the sigmoid function later. Okay, but its shape is basically it's like this. Okay, it's similar to this thresholding function, but it's smooth. Okay, so that's a traditional neuron when we developed the neural network 30 years ago, or even earlier. Okay. So why are you doing this? Okay. So let's consider the case. Basically, what we want to do is we want to, at the end, this is we have a GX, right? GX is a decision boundary. Okay, if the decision boundary, you can arbitrarily draw your decision boundary, right? That you can pretty much discriminate anything, right? For example, here, right? If you want to draw your decision boundary like this, right? Then you say, oh, my decision boundary is a circle, and then you can classify the cross and the circle, right? So this is basically give us an idea that if I can approximate an arbitrary curve, then I can pretty much generate any decision boundary, right? So in a sense, if we think about it, okay, if it's nonlinear, any curve we can actually approximate it using the piecewise linear curve, right? Right. So for then, if we think about, looks like if we have multiple linear discriminant function, we might be able to construct, we might be able to approximate any a different a nonlinear boundary, so to speak. Okay. Consider this case, right? So let's say let's only look at two-dimensional space because it's easy to draw. Sorry. Two-dimensional space, x1 and x2. Okay. So assuming this, you have linear boundary like this, and another linear boundary like this, right? So if I want to have a decision boundary, something like this, right? Assuming we want to have a decision boundary like this. Okay, so this is our decision boundary R. Okay, now how we can do it? Okay, so if we think about that, right? If we think about that, let's say you have a linear, in terms of your LDF, right? LDF. So let's say you have this, you call this, let's call this H1, right? This H2. So for LDF, for H1 or G1x, right? G1x. And if we use that neuron, assuming like this, if it's larger than 0, we give it a value 1, and smaller than 0, we give it a value -1, right? That's the thresholding function it will do. And now assume that if it's on this direction, okay, for each one, this direction give you a +1, and this direction give you a -1, right? H2, this direction give you +1, and this direction give you -1, right? So now if you look at this two decision boundary, right? If we use this structure, okay, we say, okay, the first one has one of this, one perceptron here, and the second one has one perceptron as well, right? Now we actually have 4 regions, right? This is R1, R2, R3, R4, okay. So what we can do if we simply plus this G1x plus G2x, right? We can say that in these 4 regions, we have 4 values. In this region, we would have +2, right? In this region, we would have, because in this region, this is +1. This is +1. For this guy, it's -1. Okay, for H2 is -1, so this region is 0, right? This region is 0 as well, and this region is -2, right? So in this case, if you think about it, right? So if we have this, you say like G1x, G2x, right? If each of them times 1, then plus together, right? And we can have a W0, right? And then if we do this threshold again, right? If we do this threshold again, let's say this is Gx, we would be able to particularly single out this area, right? Because this is +2, right? This one is 0. So if my threshold, I can use this W0 as a threshold, right? Then I will be able to construct a piecewise linear, right? This piecewise linear region. That makes sense? So basically, if this G1 and G2, each of them is a neuron, right? It's a perceptron like this, right? Each of them is like this. Okay, and then we use their output as the input for another neuron like this. As long as we pick this weight carefully, we are able to construct a decision region like this. Make sense? Okay, so so that's the basic idea. Okay, that's the basic idea. So indeed, the linear discrimination function or the linear regression, right? Linear regression, if we have linear regression is basically something like y. Okay, here just some additional knowledge, right? Yeah, linear regression, you have y equal to wx, right? This is linear regression. This is a vector. This is the coefficient, right? This is the scalar, right? The linear regression is the most used regression method. Now, if we say, okay, if we use this, if we say y equal to sigma, right? If this is sigmoid function, right? This regression is called logistic regression. Okay, this is logistic regression. Right. So logistic regression is again is one of the most commonly used analysis method in data analytics. Okay, in the basically this is if we don't talk about neural network, right? So the linear regression is I said in social science probably 95% and more. Their data analysis method is either linear regression or logistic regression. Okay, logistic regression is basically it looks like it's just one neuron. Okay, so that's what actually yesterday I saw a picture from some website. This is I think is exactly right. Okay, so basically logistic regression is regular Pooh Bear, right? So if they use a fancy word, we call it single layer. Actually, this is not accurate. They're trying to make the point. Single layer feed-forward neural network is sigmoid activation, right? Dressed up Pooh Bear, but it's still a Pooh Bear. It's the same. Okay, there's a question. It's your question is private. You don't need you can make it public. Let me read. The issue is that we don't know which function to go to, so we settle for combining linear functions. We somehow could use knowledge of problem space to see what function actually should be. It would be better to use that instead. You're talking about if we have particular knowledge, right? Whether we can handcraft this nonlinear function or how to combine them. Absolutely. Okay. If you do have those knowledge, you should take advantage of it. And this is what we're going to talk about probably at the end of this unit as well. And that way, because if you know exactly the structure of your data, that's probably better because it's generalized better. Okay. So, however, if you don't have that knowledge, you don't know you don't have ideas, right? So, what do we do? That's the and what is the general way we can do? Okay, so here is what we're trying to discuss. Okay, so basically, if we have a nonlinear combination, right? If we have additional layers, right? So we can say, but if you use 2 layers, we can have this L shape, right? Well, we already proved that we can construct the L shape. If you think about it, if you have L shape, right? If you can turn, that's pretty much probably using that element you can construct. You can approximate a complex boundary. Just use that element, right? You can approximate any curves as accurate as possible, right? If you use many of them. Well, what does that mean? That means you need many neurons, right? Many linear discriminant functions plus a nonlinear function. And then you probably need multiple layers, right? So that is, in essence, that is already a multi-layer neural network. Or MLP means multi-layer perceptron. Okay. Each linear function plus a nonlinear function, then to modify the output, that is called one perceptron or one neuron. Okay, if I have a lot of them stacked together, right? Stacked together either in the width and in depth, then you have a multi-layer neural network. Okay, and possibly you can construct the boundary and construct decision region like this. Okay. So that's the idea. So basically, first, with multi-layer neural networks, we need to basically, it's kind of mapping, right? We are continuously mapping input to output, and we map it non-linearly. Okay, and what we need to do, we need to learn that nonlinear design that nonlinearity, right? It's the same thing. Okay, we need to learn that. Okay. But particularly if we look at our example, the two-layer example, all we need to learn is those coefficients, right? If we can learn those coefficients, if we can pick the coefficient properly, we don't need to change the activation function. Okay, then we can actually construct an arbitrary. This is again a conjecture. We may be able to construct arbitrary decision boundary, right? Because we did an L curve, L shape, decision boundary. So we assume we can do more, right? But of course that need proof. Okay. So this structure, it's the idea is simple, but it's very powerful. Okay, as you are seeing today. It enables we can use a simple algorithm. Back propagation is actually quite simple, we will say, to learn that those coefficients. And the only thing is where is the complexity? The complexity is number of neurons. Okay, as you can see, if you want to approximate a complex curve, then you probably need a lot of neurons. Okay, so the neural network is kind of flexible heuristic technique, and we can actually prove that its learning result is consistent with the statistical pattern recognition. Okay, basically it's consistent with certain statistical classifiers. And the multi-layer neural networks is an example of the supervised learning because we need to know what we are trying to classify. Okay, we need a criteria function. Okay, similar to the LDF type of thing, right? We need to know the label. Okay, so why are we doing the neural network? Also, this one is inspired with from the biological neural network. Okay, so biologically, our brain, people have found that there are many neurons, they are interconnected, right? So, and they communicate with each other, okay? But the similarity actually stopped there. So our brain is not, we know, at least we know it's not a multi-layer neural network. It's not the feed-forward neural network. Okay, it's interconnected. Okay, we use the idea, but it's different. Okay, so the neural network is not a mathematical model of your brain, period. Okay, although it's always inspired people's imagination, right? I think, oh, we can actually simulate the brain. No, it does not. Okay, so it is inspired, but the structure, we are positive, it's different. Okay, we don't know how the brain neural network exactly work. That's actually an area of the current AI as well, because we want to be inspired more. Right? We want to understand more about how brain works. Okay, but as it is for the deep learning or neural network, it's not a model of brain. Okay. So coming back, we say, okay, multi-layer neural network, the structure, okay, we just introduced structure. So today's deep learning, right, 99% is multi-layer feed-forward neural network. Okay, the one that that is used to recognize the face. To basically, it is essentially the structure we just discussed. Okay. So it was called neural network, but now it's called deep learning, right? I think we discussed that history in the first class in the introduction. Okay, so coming back to one neuron, okay, we just formalized. The general neuron is here. This part is linear. And then we have a nonlinear function. Nonlinear function is also called activation function. Okay, then there's output. So this is input, this is output. Right, the input is a vector, by the way. Okay, input is vector because it's then this is vector multiplication, right? And then it goes through. So the output is a scalar. Input is vector. Okay, input is vector. The weight is a vector. So vector times vector is inner product, right? Or sometimes called dot product. You get a scalar, and that scalar goes through a nonlinear function. That's a neuron. Okay. Okay, so now let's particularly look at this in terms of the XOR problem. Okay, let's look at the XOR problem. XOR problem is the most famous problem when people explain the nonlinear model. Okay, the nonlinear classification, right? I think all of you are from electrical engineering, so you know what's XOR, right? XOR basically, okay, let's say the table is like this: X1, X2. If it's 1, 1, if it's the same, it's 0, right? Or let's use -1 to represent 0. Okay, it's basically two class. 1 minus 1, if they're different, okay, you get 1. If they're different, you get 1. If they're same, right? Binary, it's binary. If they're same, you get -1. So assuming this is omega 1 and this is omega 2, this is omega 2, right? It's a simple two-class classification problem. And graphically, it's like this, right? So we have 4 points to classify X1, X2. And if they're the same, right? Let's use let's use the cross. Okay, represent that 1, 1, -1, -1. Okay, so if here we have cross and here we have circle, right? Now we want to classify between the circle class and cross class, right? So then this is not a linearly separable problem, right? However you draw your line, you cannot make this separable, right? Okay. So what if we draw two lines, right? So we say first we do this and then we can do this, for example. Okay. So that would solve the problem if we use two LDF. Okay, similar to what we did for L shape. Okay, let's say so. If we use two lines, we need two layers, right? So okay, let's say how we can do that. Okay. So basically, we have here x1, x1, x2. Okay, this one just pass through with linear, right? And then you have the here. Okay, this is activation function. Activation function. Okay. And then here's we have a bias, right? Bias. So it's just one, right? The one bias. Okay. So we have two LDF. This is the first LDF. Okay. And then let's go to this. This is second LDF, right? 1, 2, 3. It's second LDF. And then afterwards, we have the third LDF. That's the second layer. Also, is this function. And this is our output. Okay, output, let's call it Z. Let's call it ZK. Okay, this one, let's call it Y1. Okay, Y2. The output is Y1, Y2. And then let's say if this one need to go to here as well. I need bias as well, right? Assuming the coefficients peak like this. This is 0.7, here 0.4. These 4 are all 1. Okay, so it's a negative 45 degree. Okay, negative 45 degree line. And this one is 0.5, and this is minus 1.5. Okay, so now we would have, so basically, assuming the linear function, right? Linear function called net J. Basically, is in this layer is the J's neurons output, right? Equal to W. This is a J's layer, so it's J's layer WJ0 plus WJ1 X1 plus WJ2 X2. Okay, we are going to use this notation from now on. Okay, so the net means that particular neuron, the output, the linear output of that particular neuron. And then we would have Yj would be the output of that particular neuron. Yj would equal to F net J. Okay, and what is F? F is activation function. Okay, and here F will define this as sine function. Okay, here it's just for simplicity. So the result will be positive 1 or negative 1, right? So this one is just for simplicity. So we use the sine function. Later we will introduce other functions. Okay, but this particular one is a sine function. Each of these circles, so okay, you ask each of circle. Each of circle is an operation. Okay, this one is basically this circle is it's nothing but a linear multiplier of this x1 x2. Okay, it's a bit confusing. This one is just parts. The reason I put it here just to show this is a linear operation of x2 because the coefficient that I put it on the line. So this one just means a linear path. Actually, if you want to just eliminate this circle, it doesn't affect anything. But this circle, particularly this circle, it means f. Okay. And all these circles, they are the same. They are the same f function, nonlinear function, which is called activation function. Are we good? And then this arrow, you already put weight on this on the line of this arrow. That's a weight. That's a W. Okay. So particularly if we call this Y1, right? So this one would be according to our notation, that would be WJ2. This is WJ2. Okay. And this one would be WJ3. wj1. This one is w22, okay, because it's the y2, so this one is w22, and this one would be w11, because this is this neuron, okay. Once we have many neurons, I know it's a bit confusing, okay, so you need to watch for those subscript and sometimes superscript as well, because although each neuron is the same, but they're in different location, right? But somehow you need to give them a name, an address, right? That's where this subscript coming in. We have, in this case, we have 3 neurons. So yes, each of them has an activation function, but in this particular structure, that function is the same. All of them have all those activation functions have same form, which is defined like this. Okay, so you see yj equal to this, right? So if we plug in those coefficients, then we can have y1 equal to f 0.5 plus x1 plus x2. Okay, y2 equal to f minus 1.5 plus x1 plus x2. Okay, this is somehow, this is LDF is like GX we talked about before, right? Okay, if you look at this, right? If you look at this, so we can, and then we look at here, right? We would know that which one, let's say which one is y1, right? For y1, so 1x equal to 0, right? If you like this equal to 0, right? 1x equal to 0, then x1 equal to 0, x2 would equal to minus 0.5, right? Here, right? X1 0. Otherwise, this. So this guy is actually this one is somehow, let's call it H1. Okay, H1, right? This one would be H2. Okay, so H1 is a linear function generate y1. Okay, H2 is linear function generate y2. Okay, then this z of k, right? Z of k is actually also equal to f. F function is minus 1 plus 0.7 y1 plus 0.4 y2. Okay. So yeah, if you look at this, right? If you look at this, we know that. So basically, there are, if you think about it, we will have 3 decision regions: R1, R2, R3, right? We divided through this 2 LDF. We divide this into 3 decision regions. Okay. So at R1, right? R1, this is on this side. So we know that Y1 is somehow, it's positive. From Y1 point of view, right? All this side is positive. Okay, it's kind of like an OR function. Okay, so why do we say this? Okay, if we plug in 1 1, right? If it's 1 1, of course it's positive, right? 1 1 is positive. It's positive 1 because this is sine function, right? If it's 1 minus 1, x or minus 1, 1, this x1 plus x2 is 0, right? But this f this with 0.5, they are all positive, right? As long as one of them is 1, it's positive. If both of them are negative 1, what do we get? Okay, so this one just quickly, okay, x1, x2, right? 1, 1 is the output. Y1 is 1. 1 minus 1 is 1. Minus 1, 1 is 1, right? Minus 1, minus 1, you get minus 1, right? This is Y1, right? Are we good? Right. On the other hand, for Y2, right? For Y2, if it's a positive, right? If both of them positive, then it's 2 minus 1.5 is positive, so that's why. But if one of them is negative, right, this is 0, then so basically you get minus 1, minus 1. If both of them negative, of course you get minus 1, right? If you look at that, Y1 is effectively an AND gate, and Y2, Y1 is an OR gate, and Y2 is effectively AND gate, right? Okay, and now we have this guy, right? So if you look at this, if both of them are positive, right? If it's 1, 1, if it's 1, 1, we say, okay, this is 1.1 minus 1, right? You would have this one is larger than this, right? So for zk, right, you will get 1, right? Let's see. Oh, okay. Sorry. There is a mistake here. This is minus 0.4. Okay, sorry. Otherwise, there's a problem. This is minus 0.4. So in that case, let's look. Okay, if you have 1 and 1, you actually have 1, 1. You actually have the negative 1, right? If you have 1 minus 1, 1 minus 1, so here is 1.1, right? So you actually have positive 1, right? Both of them, you see, here. Okay, you see both of these, you get 1 minus 1. So both of them would map it to plus 1, right? Then if both y1 and y2, they're minus 1, right? Minus 1, minus 0.7, and this is minus 1 is positive 0.4, but or you need to minus 1, and then at end you have minus 1, right? So what we just proved is that this neural network exactly accomplished our task, right? It's basically the output. We are able to classify omega 1, right? And omega 2. Okay, you see the label, right? This is omega 1 label, and this is omega 2 label. Okay, make sense? What's the difference between yi and zk, right? This y, so here, if you look at it, right? So this is input layer, okay? This is input layer, right? This layer is hidden layer, right? This layer is output layer. So what we say, what we're seeing now is a 3-layer feed-forward neural network. We have one hidden layer, right? So input layer is X, right? Here we represent by, the input is X. Hidden layer represented by Y. Output layer here we call it ZK. That's a notation, okay? Are we clear? Okay, and we can have many hidden layers. If we want, we can have many hidden layers. Okay, but this particular one, we have one hidden layer. Okay, let's look at the slide. Okay, so this is what we just discussed. Okay, and then so this is pretty much the idea, right? So basically we have this geographically, right? If you say this Y1 is like this, Y2 is like this, right? Then you make this negative, make this positive, and then your output is like this, right? This is how it geographically is constructed. Using 3-dimensional, the height of this represent the class, okay? Because at the end you have threshold, right? Once you have this, you say, okay, you cut it, then this middle line pop up, right? Here. So this is our handcrafted neural network to solve the XOR problem. Make sense? Okay, this problem was solved using perceptron in 60s. Okay, that's a neural network, the start of the neural network, and now it's still this. Okay, there's no difference. Current neural network. Okay, so here the structure, right? So if we examine that, here's the structure we have explained. That this is input layer, this hidden layer, this is output layer. Okay, this we use X, Y, ZK. Okay, and neural network has 2 modes of operations. Okay, the first the first one is training. Okay, this is actually not just neural network, right? All the machine learning method, the first step is training. Training is basically to figure out the parameters. Okay, figure out all this W. Okay, -1, 0.7, -0.1. How do we get there, right? That's called training. Okay, and more specifically, when we say training, oftentimes we mean to use data to train, right? Use label data. We are trying to design some criteria function and then try to, using that criteria function, we try to find out the best way to satisfy our criteria function, that's training. And then the second mode of operation is also the same for all machine learning methods. We have trained network. Then we would do classification, right? Classification would be, in this particular case, is feed-forward. Why? Because we this is up is feed-forward, right? So basically, we have an input. Give me a sample, I'll give you the result, right? That's a feed-forward. And another thing, is particularly for this network, is the data, right? The computation always go forward. There's no feedback, right? In this one, there's no feedback. Okay. It's called feed forward. But the training is oftentimes is backward because first feed forward, we get a result, right? Then using result, we go backward to train our network. Okay, we'll get there shortly. And then the basic element is called neurons, right? Each circle here is a neuron. Okay, this one, the input, if you have to call it, you can call it linear neuron, okay? So so it's basically it's weighted combination. We have weighted combination. The neuron is mainly two parts. One is the linear LDF part, right? The linear combination of the input of that neuron, and the second part is activation. Okay, and all of them we have bias unit. Okay, and then there's a synapse. Synapse is basically represent the weight. Okay, it's part of that. Okay, so the neuron, each neuron is consists of the the bias unit, synapse, right, and the particular input. Okay. So here is some notations. Okay. This is the input layer. This is a hidden layer. Hidden layer we call hidden J, right? So you can have multiple J, right? You have and then output K. This is the kth output. You can have multiple output as well, right? If it's two classes, you can use one output. But if you have multiple output, you can multiple class. You can have multiple output. Okay. And here is the full formulation, right? Then you have the number of the hidden node here. This one is only one hidden layer, okay. And then you have number of input. That's we already discussed before, right? That's number of features, basically the feature space dimension. And then you have C is output. How many categories you have? Okay, that's C. Sometimes we call K, right? C. Sometimes it's the C class, K class. Okay, depending on particular literature you're looking at. So for each neuron, we have two steps. The first step is net activation, right? This is the J's neuron. In J's, basically, this is for hidden layer, right? This is for hidden layer, okay? Because here we're still talking about this 3-layer neural network. This is for hidden layer. Hidden layer, the linear output is this. This is the output layer. Output layer, the linear output is this, right? It's a linear combination of its input. Its input is the output of hidden layers. That's Y, right? And the output, so this is the key, okay? So the neural network, the key is this activation function, right? So you might think, okay, what if I don't use nonlinear function? What if all of these are linear, right? Can you have a linear neural network? The answer is simple. Yes, you can. Okay. However, if this is all linear, then basically you can put all together. It's a huge. It basically become one linear function. Okay, it's equivalent to one linear discrimination function. Okay, the combination of multiple linear discrimination function is one linear discrimination function. That basically saying that if all this nonlinear function you replace with the linear, then it can collapse to one linear function. Okay. But is it still useful? What do you think? Do you rather use one linear function or multiple linear function like linear neural network? What do you think? You're using one, why? Less computation. Yeah, that's very good. Yeah. Anyone argue you using multiple? No. I would argue to use sometimes you might want to use the multiple. And in terms of less computation, not necessarily, I would say. Right? Because you think about it, it's like a linear function is like a matrix, right? And then if I have multiple layer, it's like I'm decomposing that matrix, right? One matrix can be the multiplication of multiple matrix. Each of that matrix might be a special matrix, right? Might be sparse or simple. My question, ask me restate my question, right? I'm just trying to challenge you. I say, okay, if all these guys are linear, right? Or all these activation functions are linear. So it's equivalent. If we put all of them together, it's equivalent to one linear function, right? We can basically if you think about it, right? You just remove this f, right? Because if it's f is linear, then basically it's fx equal to x, right? If fx equal to x, if you remove this f, as you can see, if I remove this f, if you multiply this in, it's actually still a linear function, right? Right? It's think about it. If I remove this f, right? If I remove this f, right? Now what happened? You can just multiply this in. This still a linear function, right? It's not. It's basically it's a single. It becomes a single linear function, right? If you multiply it in, right? So if you don't want to treat that many, weight, in general, right? It's simpler, right? You just use one neuron would be good enough, right? So that's why the answer is saying, okay, if I use one, probably less computation, right? But I'm arguing that sometimes if you write this down like that, might give you some advantage, right? Structurally, because each layer has its own structure. It might seem redundant, but for a particular problem, it might give you some advantage. Okay. Okay. So that's I will come back to that shortly. Okay. I could have given an example, but that would take me too much time. So, but I will come back to the concept later. Okay, come back to concept probably in next couple of slides. Okay, so that I can conceptually answer that. Why? Where just the structure of you think about it, right? If you have two sparse matrix multiplied together, it might be a full matrix, right? But each of them would be simpler to compute. We have this all the time, right? Like, if you multiply by 5, that's similar to multiply by 10 divided by 2, right? Would you just multiply by 5 or multiply by 10 and divided by 2, depending on how you implement that, right, in hardware? Okay, so that's just some insight. Okay, and actually, but regardless, we coming back to the structure issue, right? We understand this single hidden layer neural network now. Okay, so if you look at this, it's just concatenate all these layers, right? If you have more layer, just keep writing this equation. Okay. Okay, here is basically, so how many layers is good enough? We're saying that we want to, motivation is we want to approximate a boundary, right? Basically arbitrary boundary. So the boundary can be any shape. We L shape is one. The other one is actually those two things not even connected, right? So how many layers do you need? Okay. Here's the conclusion. Okay, it's called universal approximation theorem. Okay, I'm not going to write it down here, but it's simple. How many hidden layers do you need to approximate any function, right? The answer is you only need one hidden layer. Okay, basically you only need 3-layer neural network. You can approximate any boundary, provided you have, as long as you have enough number, sufficient number of hidden nodes. You can approximate any function. The hidden node, you can be a sine function, or can be sigmoid function, let's say. Then you can infinitely approximate any function. Okay, we actually, this is not a surprising description, right? Think about the Fourier transform. Fourier transform is that any continuous function can be approximated by linear combination of all harmonic functions, right? The harmonic, let's just say a sine function or cosine function, or E, J, X, right? That's the essence of Fourier transform, right? For electrical engineering, I think that's your bread and butter, right? So basically, for any function can be decomposed to a linear combination of complex exponential function. This is the same. We're saying that any function can be approximated by this type of kind of shifted, right? The linear combination of all these guys. That's the most important conclusion in the 90s in terms of neural network, because our computing power is limited, right? And neural network is not easy to train, okay, given the computer at that time, right? Moore's law, right? If you think about 1990, right now it's 2021 actually, it's 20 years, right? 20 years, if you think of Moore's law, you go back to say, okay, what would be the computing power at that time? So you see my point, right? So, okay, we try to minimize the number of layers and number of nodes, right? So given that, so it's not surprising in 90s, we say, okay, let's not make things complex. If we use neural network, let's just use one hidden layer, or at most 2 hidden layers, because that's enough. Right? In a sense, it's the same. If you have multiple hidden layers, it's equivalent to have one hidden layers, right? Or it's similar to what we did for linear functions. I say, okay, however many layers you have is the same as a one linear layer, right? It's redundant per se. Here is also, we're saying that if you have multiple hidden layers, it's redundant. But today, that's what we are doing, right? Otherwise, we wouldn't call it deep learning, right? Why do we have so many hidden layers? That's kind of similar to what I said in the linear things, because each layer is kind of decompose the features. For example, I think in the introduction, you go back, look at my slide, right? So basically, first layer, I extract edges. Second layer, I extract kind of corners. The next layer, I extract shapes somehow. Right? It is redundant, but it somehow gave us, structure of the data, structure of the problem. Make it simpler, or make it more expressive. So if you use one hidden layer, can you do that? You can still do that, but it's kind of collapse those different expressing power. Okay, mathematically, it is, you can do that. Okay, think about why I say, okay, in terms of linear, for matrix, right? If you want to decompose it to multiply of two matrix, it's the same, but each matrix might serve a different purpose, right? In linear algebra, the whole linear algebra is about matrix decomposition, right? Okay, we say, oh, eigenvalue decomposition. Can we decompose the matrix into a rotation and then the identity matrix, right? If we do that, we're happy, right? Because each matrix has specific meaning. So the multi-layer also would serve that type of ideas. Okay, of course, this is kind of not beforehand knowledge. This is the afterwards. Okay, after say, oh, why it works, then people look at each layer. Looks like it has this type of property. But unfortunately, we don't know how to get there. Okay, mathematically, it's just automatic. Given the data is trained like that, the problem is we have very little way to control each layer. Okay, so that's the general status. Okay, conceptually that's the case, but unlike the linear algebra or the linear system, we can have closed form analysis, exact analysis of those type of decomposition. We can design those decomposition with certain criteria function or with certain property. In neural network, unfortunately, we most likely we don't. Okay, that's the issue. Okay, I think it's time to take a break. Come back at 4:38. 4:38. Okay. Okay, so let's continue. The second half of today is basically will be the algorithm, the backpropagation algorithm. I will try to introduce that. Okay, but anyway, now we have a big picture, right? Big picture in terms of the multi-layer neural network. So here is the graphical representation, right? So basically, each of this one is a neuron and could represent something like this, right? We already have one example. And then for whatever shape, right, arbitrary shape of decision region, we are able to use this guy to approximate an arbitrary shape decision region. Okay, that's what we said. That's a universal approximation theorem. It can be proved. Okay. So we will be talking about backpropagation. Backpropagation is basically, let me explain the principle first, then we'll go into the detailed rapid expression. Okay. So the idea is the same as what we did before, right? It's basically a gradient descent. Okay, it's gradient descent algorithm. So what do you do? So you first, we need first to have a arrow function, right? Then we take the derivative of that arrow function to all these coefficients, right? If we find derivatives, then we complete our task. Then we can have one iteration, right? And afterwards we compute that again. Okay. So the backpropagation is a gradient descent optimization method, and particularly there's one method. It's called the LMS, right? Least mean square. It's again either to train a neural network or to train whatever machine learning method. You don't have to use LMS. Okay. So you don't have to use LMS, but it is a very popular method. So the least mean square arrow is basically to use the single arrow to represent the summation of the arrow or average arrow. Okay. LMS is for per sample, right? It's per sample arrow.
Sorry, sir. Are you sharing your screen?
You're right. Yeah. Okay. Yeah. So sorry. So the first one is the graph I wanted to show you is this arbitrary decision region, right? Because each of them has this type of linear decision region, and multiple linear decision region can form an arbitrary decision region. Actually, for any type of decision region, you can use this guy to approximate, right? That's a universal approximation theorem. And then we're talking about the LMS. Fundamentally, the LMS is to use the single sample error, stochastic simple sample error, to represent the average error. Okay, so the average error is all training samples, right? If we have a million training samples for each of them, we'll compute the error, and then with that error, we try to adjust that, right? We had examples when we do the linear discrimination function. It's the same. So if you use LMS procedure, then for each sample we compute the error. Okay, for each sample we compute the error, and then using that error we adjust our coefficient, right? The parameters. Okay. So the gradient based. Okay, so the LMS is basically is simple. Okay, and for all learning algorithm is already have this type of advantage, right? So it's a wide problem to if you pseudo inverse, you do pseudo inverse. What if that pseudo inverse is kind of singular, right? You cannot find a good pseudo inverse. Also, if that matrix is too large, you need large memory. If you use iterative way to do that, and then you don't have to, you don't need to deal with the large matrix. Okay, you just adjust each component individually, right? Although at the end, the effect is multiplication of the big matrix, and you are effectively solving that inverse problem, but you don't directly solve, do the matrix inversion. Okay, that's the advantage. And also, it can work on online data LMS because it's single sample based, right? It's also called stochastic learning, right? The LMS is also called stochastic learning as opposed to batch learning. Okay, so the LMS algorithm is representations like this. So basically, for each k is the k sample, right? For each sample k, you see, you're computing the error for that particular sample, right? For each sample, you're computing that error. And this is the gradient, right? The gradient of that using that error. So if it's average error, you would have sigma here, right? Average error, you'll have sigma here. So if you replace that sigma with a single sample, and then you cycle through all the samples, that's the LMS algorithm. Or it's called stochastic gradient descent algorithm. Okay, any questions regarding this LMS? LMS is basically single sample gradient descent algorithm. Okay. So now let's look at the formulation, particularly for the back propagation. Okay. So the LMS, okay, LMS is a traditional. It's actually developed in signal processing or adaptive signal processing context. Okay. Okay. In learning context, this one is actually if you say, okay, what's the algorithm you are using, right? It's called SGD, right? So what's GD? GD is gradient descent algorithm. What's this S? Stochastic, right? So this stochastic part, what's stochastic? I mean, single sample, right? You use single sample, right? If it's only gradient descent, basically it's kind of a batch. Okay, you would use a batch. But of course, in practice, it can be more complicated. You can do in between, right? You can use mini batch. You can use several samples together. That's also kind of stochastic gradient. Well, why it's called stochastic? Because single sample error is random, right? It's more random. If you average the error, that's actually close to mean error, expectation of the error, right? But if you use single sample, for sure, that error is stochastic, is a random error. Okay. Okay. So now, what we want to talk about is this back propagation. Or called BP algorithm. Okay. So the first thing we need to do, right, for any learning algorithm, what's the first thing we need to do? For learning algorithm, in general, right? This is general. What's the first step for any learning algorithm? Get a prediction. But even before that, right? Find the error that's close. Almost there, right? But what's the first thing you need to figure out, or you need to define? Loss function. Exactly, loss function, criteria function. Of course, first you need to decide. Even before that, you need to decide that it's here we're talking about the multi-neural network, right? So basically, we need to decide network structure, right? That's structure. For example, how many layers? Those called hyperparameters, right? We need to have hyperparameters. And hyperparameters, and that's we need to set it ourselves. Hyperparameters, it's although there's a study how to learn hyperparameters, how many layers, how many nodes, right, in each layer, but those are actually it's hard to learn, and that's part of the alchemy of the deep learning of neural network or machine learning. Okay, you try something and see whether it works. That's pretty much it. But that's take for granted, right? Then the thing is a loss function or error function, right? Or we call it risk function, right? Or cost function. It's the same thing, right? It's a criteria. Okay, basically you need to have criteria when we say, okay, what's your target, basically, right? This is your criteria. Or it's actually your target, right? This is your target. You have to have a target when you train. You have to have target. This, right? And here we're doing supervised learning. And actually, regardless it's supervised or unsupervised, you always need a loss function. If you're unsupervised, you also need some loss function to optimize. But particularly, this is a supervised learning. Okay, the BP algorithm is supervised learning. Okay. So supervised learning, that means it's labeled, right? You have target. Let's say the output is ZK, right? But we want it to be TK, right? ZK is what we get. TK is what we want, okay? Or your label or whatever, okay? So now we need to define the loss function, okay? The loss function has many, it can be different things, okay? But here, just for the purpose, we introduce this algorithm, okay? And it is, actually in your practice question, you will see other form. But here, let's say this is the parameter, our weight, right? Here, what we use is the mean square error here, MSE cost, right? Loss. So we look at the mean square error, K. This is the assuming there's a C classes, right? We look at all the classes, TK. TK minus ZK squared. Okay. Or in vector form, that's a half T minus Z squared. But this is for all classes, right? For all classes. And for all samples, you have another sigma, okay? So once we have a criteria function, then for gradient descent, it becomes simple, right? Gradient descent is they say, okay, what would be at any iteration, the adjustment of your delta W would be the negative. This is learning rate, right? This is gradient descent, right? This is gradient descent. So basically we say, okay, at iteration m plus 1 equal to, I didn't use k because k is already used. Okay, I didn't use t. I don't use t because t is already used. So I use m plus, right? That's what you do, right? So the whole, the core of BP algorithm, right, or gradient descent, is basically compute gradient. Okay, if it's a gradient descent, it's very trivial, right? So, but why is the BP algorithm so special? Okay, after we discuss this, we will say that it's not special at all. It's a little bit complicated because it needs to use your calculus 101. That's a little bit complex and use compute derivative directly. It uses a derivative computation formula that is called chain rule. Okay, so the BP algorithm, the whole sophistication is in chain rule. Okay, chain rule of the derivative. When we say chain rule, that means we have a chain, right? What is that chain? So, okay, basically the chain is that network. Okay, network look like this. Okay, here from the output, what is the output? Output is z of k, right? From z of k, we have jw, right? Along with this tk, right? Tk minus zk. And then we get JW, right? The TK, what is TK? Label, that's a label. That's where we get beforehand. Okay. How do you get Z of K? Z of K is coming from net K, right? How do we get net K? Net K is coming from Y of J, right? Where did you get Y of J? Y of J come from net J. Where did you get net J? Okay, here, if we assume it's a one hidden layer, right? The net J actually comes from the input. Or from, let's say, the previous hidden layer. Previous hidden node, okay? Or from previous hidden node. But as long as we know how to do this one layer, one hidden layer, we know how to do multiple hidden layer. Okay, we'll see. So now the question is, what's a function relationship, right? Z of k equal to f net k. What is f? It's a nonlinear activation function, right? And how do you get net k from yj? Right? You will have to have wkj, right? Wkj multiply all this yj, right? It's a linear function of yj with coefficient wkj. Wkj is something we're interested in, right? Okay. What about y of j? Y of j equal to f net j. Right? Now what is net j? Net j, you actually here, you basically, here, let's make, you need this, right? You need this w. This is wkj. This is wji. The first subscript is the output node. The second is the input node. Okay, this is the same, right? J is the input, K is output, right? Okay, and this is hidden, right? This is hidden layer. Okay. Okay, so we need to find the derivative of J to all these W's. Okay, first, okay, let's look at the first is from hidden layer to output layer, right? Let's do this step by step. Right. Okay, let's compute it. Partial J, partial WKJ, right? How do I find out this, the derivative of this guy to this guy? This is the chain rule we are going to use. We're going to first compute its derivative to partial net K, right? And then times its net K by partial WKJ, right? Here we use the chain rule, right? The derivative of the chain rule, right? We have a name for this. This one, we call it delta. This one minus delta K times partial net K partial WKJ. Okay, here this delta K is defined as partial J partial net K. Okay. So it's basically two part. Okay, what is delta K then? If we want to compute delta K, right? Delta K equal to partial J, again, let's use chain rule, partial ZK times partial ZK by partial net K. Okay, partial J, partial ZK, right? This is straightforward. It's two. We pull this two here, right? Pull this two here. So it's basically 2 TK minus ZK. Right? This is minus, then it's positive. So it's TK. This one becomes TK minus ZK. Now assume here, we assume C equal to 1, right? Just make it simple, assuming C is 1, right? If multiple, just put the sigma there. It will work. Okay. So this one is an error, right? The error times. Basically, that error is the derivative, right? If we look at this, the error is the derivative against ZK, right? We need to compute because TK is known, right? TK is known, is our label, right? So this derivative to ZK is a function of the input and also function of the W, right? Function, the ZK is a function of the coefficient. Yes, the TK is the ground truth value. It's our target. It's a label, okay? Times partial ZK, partial net K. What is that? ZK and net K, what's the relationship? That relationship is exactly the nonlinear activation function. So it's F prime net K. Okay, this is means derivative. Is that clear? Okay, now we need to compute this, right? What's the relationship between partial net K and WKJ? Okay, if you look at our formula in terms of relationship, right? Yj net K equal to the linear combination of all yj, right? It's a linear combination of all yj. Therefore, this partial net k, partial wkj, right, equal to yj. Not yi, it's yj. Right? Now, wkj is the coefficient of yj. Right? The net k is a linear combination of all yj, right? It's a linear combination of all yj. So what's the weight of that particular yj? By definition, that's wkj. Therefore, this guy equal to yj. That's clear? Okay, now we can come back to this, right? Then, okay, so this guy is minus this, minus delta k, right? So therefore, basically, we get delta wk. This is one coefficient, right? Wkj equal to what? It's minus this, right? It's minus this, so it's actually delta k times this. Okay, so if we put all together, eta tk minus zk times yj, right? We are missing. We still need to do this. Okay, sorry. Times f prime net k yj. Okay, this whole thing is delta k. It's actually minus delta. Let's say, yeah, it's delta k. It's not minus delta k, right? So, or this one is actually equal to eta delta k yj. You see here, wkj's derivative is delta k times yj. So now we have the derivative of the coefficient between hidden layer to output layer, right? This is the last layer. Okay, but we still need to find out the next one. The second step, I need to go down to find the derivative of the next layer. Okay, so this is the first step, hidden to output. So the second step, from the input layer. Okay, here's input. Actually, it's a previous hidden minus one. Okay, previous hidden is the same to current hidden layers. Right, previous to current hidden layers. What is that? That is partial j, partial w, ji. This is the j's hidden node. Okay, its output is yj, right? Its linear output is netj. So again, let's do the chain rule again. Partial j, partial yj, right? It's because that's the output of this guy, and then partial yj, partial netj. We're doing the similar thing, right? As before, times partial netj, partial wji. Okay, so again, let's we need to compute this guy, right? To yj is basically is another layer. Okay, so let's compute the first term first. Partial j partial yj equal to partial j partial yj here. Okay, we just plug in the half. This is tk minus zk squared. Okay, this whole function. This is again we do chain rule. We first do zk, right? We first do zk. We first do this, then we have this minus tk minus zk, right? Tk minus zk. Then zk need to is partial zk by partial yj, right? This one is actually two-step, right? Because between zk to yj, there's a immediate intermediate step, which is net k, right? Net k. It's actually partial zk partial net k times partial net k partial yj. Right. Okay. That we got is partial tk minus zk. This by this is s prime net k times this net k to yj, right? Net k to yj. Net k is linear combination of yj. We just did that. This is wkj. Okay, so the net k partial derivative to yj is wkj. Its partial derivative of wkj is yj, right? Because these two multiply together, right? If you compute partial derivative to y's, then the result is the other. Okay, so if you look at this, actually, yeah, basically it's we similar, right? We share this guy. Right? If you think about it, we actually share this guy. This whole thing equal to minus, this is delta k, right? Times w k j. Okay. So we have this, see, this delta k is basically it's partial j by net k, right? So the thing is actually this. If you think about it, what we're doing here. So from here, we find this here, right? This is delta k, right? Delta k. Okay, we are propagating that delta k. Okay, how? That's our next step. So this whole thing is delta k, right? Okay, now we have delta j equal to f prime net j. Okay, this is defined as f prime net j times delta K times WKJ. Okay, if you look at delta's definition, okay. So this is partial J by partial net K. This is actually partial J it's actually this part, okay. Then we have this delta WJI. If we look at that, we write it down, then I will explain. Okay, equal to eta delta J times XI. Okay, or if you write it, it's delta K times the KJ, right? KJ times F prime net J times XI. Why? This XI is this is Xi, right? It's similar because net J is a linear combination of Xi. Okay, so you should take that derivative, that will be Xi. Okay, and this whole thing is delta J. Okay, so here, by doing this, we are propagating delta K to the next layer, going down, right? Back propagate become delta J. Okay, so if we look at each layer, right? Each layer, the form is the same. See? Okay. So particularly here, this one is only one output node, right? If we have multiple output node, it's actually what simple thing to do is here sigma K, right? You just add all this because you have output. If you have K node of output, you just add up all those delta. Then you get the delta of the next layer. Okay, so let's say this Xi is not the input, it's the previous hidden layer. Okay, all that, then you would redo this step 2. Okay, so basically that's delta K, and then you propagate here is delta J. Okay, let me pause a second to appreciate how this is propagated. Okay. Okay. This one, if you think about it, this is the initial delta, right? This is delta, can call it delta 0 or whatever, right? So this is the initial error, right? The initial error is back propagated through this backwards, right? Through this derivative of your activation function and your coefficient. Okay, now you get this. Then the next layer is the same, right? So this guy serve as this arrow, right? This, but you have multiple of this arrow. This multiple of arrow is still through all the coefficient related to that fit into the bottom layers. Okay, the lower layers. So basically, assuming at certain layer you have multiple, let's say delta K1, right? Or let's say this is delta K1, yeah, delta K2. So let's say it's actually, yeah, delta K. So you have, let's say it's actually no, because this is, you have K nodes, right? Here, so this is K, this is K minus 1, K plus 1, right? So each node you have an arrow, right? Each node you have an arrow. So basically this is this arrow, right? This arrow. So if you have multiple arrow, right? You have multiple arrow, how do you propagate? This is the arrow, right? This is the last one. This one is actually, as we call delta 0, or let's call it epsilon, epsilon K, right? Epsilon K. And then you back propagate through all things related to this K, right? You have this, if you back propagate, this is WK, WKJ basically, right? WKJ, because they are related to YJ. This is WK minus 1J, right? All of them are related to YJ. Here's YJ, right? YJ. And this arrow to here, it becomes delta, you get your delta K, right? You get delta K, you see? Because here's the YK, right? This is kind of Y prime, okay? Because you have that activation function, right? Here, let's say it is F prime, right? F prime net K. Okay, it's basically it's Y node YJ, right? And then you get the delta K. Okay. So so here is actually this is from epsilon. Then the okay, so from epsilon, if you put together, actually you get delta K, and then you have several of this delta K, right? You have several delta K, and then from next layer, right? Again, F prime, you kind of it's again you get delta J, right? You get delta J, and those delta J again you back propagate to next layer to adjust the coefficient of the lower layers. Okay. If we look at the right, if you think about it, first I have an arrow here. Right? This arrow is used to adjust, this particular coefficient, right? And then also there's give you delta J, and then delta J is also put into you have here, so you have delta here, you have delta, and all this delta feed into here. Okay. Yeah, this one has more, so it's easier to look at. So you have all these multiple guys, right? Multiple guys, and then you would first fit into here for a particular y, right? If it's the feed forward is to find out the output, right? From here and then multiple one get to here, then multiple this get to particular this. But if you go backward, all these arrows, right? They have relationship with this particular coefficient. Okay, so basically the arrow here is related to all arrow there, right? So that arrow is delta J, and then that delta J is used to compute this particular W, the derivative of the W. Yes, you can consider delta is the arrow propagate to each layer. So first is TK minus ZK, right? And then propagate to the next layer, it becomes the delta delta K, right? And that next layer is delta J. Delta J is for in this case it's between the input layer to the hidden layer, right? So but assuming it's J minus 1 layer, then you can still propagate to J minus 1 layer as delta J minus 1, right? The whole idea is this chain rule, okay. So here, you say here is the delta K times this. This is propagate back, right? You accumulate that arrow, but then you need to go backwards, go through this function, right? Go through this nonlinear function. Okay, so you have eta delta J xi. And in the first layer, right, it's eta this guy, right? Then this whole thing is delta K, right? This is delta K, because this delta K is partial J by this. Delta is basically it's delta J is this. Okay. Let me just write that down again. So basically, the definition has been okay. So basically, at the jth layer, delta J equal to J partial is negative partial J by partial net J. So the relationship here, right? The relationship is basically is this, right? So basically we say, okay, this partial J by this, then so delta J is equal to sigma delta K times WKJ that times F prime net J. Okay, here's the relationship. Okay, so if I write one more step, right? One more step would be WJ. Let's say go down is J minus 1, right? Minus 1 would be partial J, partial net J minus 1. And that would equal to sigma delta J times WJ here would be J minus 1 layer. Okay, let me see. This is the case layer, yeah. This is the between j to j minus 1. It's actually this is I think if it's multiple layer, we need to the notation is I shouldn't use this notation. Okay, let me make it clear. Okay, so there's a little bit problem here. So assuming this is a hidden layer, that is called H, hidden layer H, right? This would be hidden layer H minus 1. Okay, hidden layer H minus 1. Then it would be because hidden layer, this is this is which node, right? This also hidden layer H minus 1, right? Because in H minus 1 layer, there's many nodes. This is particular node, right? That would equal to sigma delta JH. Okay. Okay, here, I think this 2J is different. So here I should use I. Okay, bear with me. Okay, so the notation is a little bit complex because this I is not necessarily the same as this J, right? Because this is at H minus 1 layer, this is at H layer. So you would sum up all J, right? All those arrows together with this W, this would be H minus 1 layer W. And the relationship between J and I times F prime net. This because this is the ith node, so net I. This F, I don't need to use it, have a superscript in terms of it identifies layer because this F is the same, right? But this W is not the same. That makes sense? So the back propagation is basically the back propagation of the arrow, right? So basically the arrow at top layer, how does it affect the equivalent arrow? It's actually, you know, it's called arrow is somehow it's a bit misleading. It's a virtual arrow, okay? Because this is basically what happened in top layer, right? How does it affect what happened in next layer quantitatively? Okay, but the format, it looks like arrow. It's for that particular layer, looks like an arrow that can be used to adjust, used to compute the gradient to adjust the coefficient of that layer. Any questions? Right. If we think about it, this is nothing but, if you think about the definition, right? This is nothing but a chain rule. So this one is this one is just simply this, right? And this one, the relationship between this net H minus 1 and net H is through this, right? Through this and through the F. That's, you know, if you think about the forward relationship, it's not hard to understand the backward relationship. Okay, so or this one is, you know, if it's the first layer is actually indeed arrow, or this one we also call it sensitivity. Sensitivity of error to a hidden unit. Right, you see, this is J, right? The derivative to this layer is a sensitivity. So this sensitivity is related to the upper layer sensitivity. Okay. So what is a necessary condition for this gradient design algorithm to work? What is a necessary condition? Convex, or which one is convex function? Yeah, the whole thing, we are minimizing this loss function. But if you look at carefully in this computation, right? For this derivative to work, we have to be able to obtain each element, right? For example, right, here is let's say first layer, right? We want to find out this delta kj, right? If this eta is the learning rate, right? What we assign, we know that, right? Yj, we also know yj, right? Because that's from the forward calculation, right? That is the delta k. How do we compute delta k, right? Delta k is the error, right? So we do forward first, then do backwards, right? So forward, tk, that's a label, we know that. Zk, we can compute, right? Because once we initialize the network, we know that. But do we know f prime net k? Do we know net k? Net k is the linear output of the output node, right? We know that because we can do the forward, right? Then the question is, do we know this derivative, right? The derivative of net k. Do we know that? Are we sure we know this derivative? And the answer? Do we know that derivative? If we select the proper function, okay, one of you said, what do you mean by proper? Is sign function a proper activation function to do this? Because in our actual example, we use sign function, right? It's a nonlinear function, it's accomplish a task. But is that a good F function, activation function? Is it? So is sign function, can we use a sign function to apply this backpropagation algorithm? If we use sign function, what could happen when we do this backpropagation? What's the derivative of the sign function? It's zero, right? It's zero almost everywhere, right? Only at one point, there's no, at point zero, there's no derivative, but otherwise it's zero, right? So what happened if f prime equal to zero? The sine function, that the derivative would be zero everywhere, right? Slope, right? So if you have this function, what's the derivative here? Zero, right? Derivative is zero. Derivative is zero here, right? F prime, right? What about here? There's no derivative. It's discontinuous, right? All arrow zero. So what does that mean? That means you cannot use this algorithm, right? The whole idea is depending on, okay, this derivative give me, let me know where can I adjust my coefficient better, right, toward the better direction, right? And if the derivative is zero, there's nothing to adjust, right? So we cannot use we cannot have an activation function that with the derivative zero. Okay, so the sigmoid function would be like this. Okay, then it's different. What do you mean? Is this the case of argmax? You can compute the loss, but you cannot compute the derivative. Because if it's a sine function, forward operation, there's no problem, right? If you have input, we can always compute the linear combination, or we can always find out the sign of the output, right? This can go on forward. But once we want to go backward with derivative, we do back propagation, we compute the gradient. There's no, we cannot do that. Okay, we are not able to optimize that function using gradient descent method. Okay, but it doesn't mean there's no solution. There is a solution, right? Like we explained in XOR, we give a solution, but it's just that you cannot use this gradient descent algorithm to find that solution. Okay, it's you cannot use gradient descent to do learning. That's all. Okay, then we say, okay, let's do something smooth. Can you do that? Yes, that's yes, we can do that. Okay, but what is a good activation function? What could be the problem, right? So that's actually it's people you can come to a long way to get a simple solution. Okay, we'll discuss that more next week. So yeah, we have some equation to digest this week. Okay, so your lab3 is already available, right? You can start to do that. Okay, so that's for our materials for today, and I will see you next week.
Thanks, Dr. Zhang.
Thank you.